microphone to Professor Srinivas Chakravarti.
Hi, good morning, Madhav. Good evening, the audience. So it's my pleasure and honor to introduce Professor Madhav Marathe. Professor Madhav Marathe is an endowed distinguished professor in biocomplexity, director of the Network Systems Science and Advanced Computing Division, Biocomplex Institute and Initiative, and a tenured professor of computer science at the University of Virginia. Dr. Marathe is a passionate advocate and practitioner of transdisciplinary team science. During his 25-year professional career, he has established and led a number of large transdisciplinary projects and groups. His areas of expertise are network science, artificial intelligence, high performance computing, computational epidemiology, biological and socially coupled systems, and data analytics. Over to you, Professor Marathe.
Thank you very much, Srini, and thank you very much for the patience that the audience has shown in getting my slides up. Before I start, I want to thank Sayan and Sunetra and Mahesh and Ravi, who kindly invited me to join the Complex Systems Initiative that you folks started. Srini is somebody that I know for a long time. In fact, he was my batchmate back in IIT. And believe it or not, this is my first talk at IIT after leaving IIT in 1989. So thank you very much for allowing me to do this. I'll have about an hour, Sayan, you think, or Srini?
Yeah, that's right. Maybe
Okay. 50.
Sayan,
you can give me a 5-minute warning and then we can continue.
Okay.
Okay. Let me also thank our group. This work is certainly not work that I've done alone. In fact, the group has played a critical role in everything that we have done, and my contributions have become smaller and smaller over the years. I think it's thanks to the folks who are all shown here, but also my collaborators in Albany, New York, where my advisors are, at College Park, in particular Arvind Srinivasan, who is also my batchmate and a close colleague of many of you, and colleagues at Princeton, Simon Levin and others, Stanford and Virginia Tech, and many other places. We've also been supported by many grants, and I want to acknowledge their support as we do this work. So let me start and tell you what I will speak about today. I'm going to break my talk into pieces. I'll try and introduce multiplex co-evolving networks as an object of study. And in fact, I'll try to focus on dynamics over networks rather than only structural properties of networks. And then I will also discuss the big data problems that arise when you study real world societal problems and take examples from various fields, and finally focus on epidemics and epidemic science as a topic where I will try and articulate and elaborate on the way techniques are used. One of the things I would like to do is to convince you that algorithmic solutions are often embedded into these complex workflows, and large-scale simulations really are needed to solve these problems because of the interactability results that are abound in this field. So with that, let me start. So as I said, we are going to study massively interacting systems, and they are networked, which means that you have multiple agents. In our case, anywhere between 10 to the 4 to 10 to the 16 agents or entities, and they're networked. These networks are irregular. They don't have the typical symmetry properties one assumes. They also evolve in time. And most importantly, they co-evolve. And I'll say a little bit more about all of them. And there are a number of application areas that we have studied, from energy systems to transport, to natural and human-initiated disasters, to epidemic and public health. And as I go along, I will give you a few examples. I started studying this back in 1994 or so when I joined as a postdoctoral fellow at Los Alamos. I had finished my PhD in Albany. Los Alamos had started doing this kind of work a few years before that. And there are a number of programs that I want to highlight, and then we'll move to specifics. The program called Transcendence that my colleague Chris Barrett led there. So the first sort of real example where these large-scale models were used to study an important societal question, which I will describe. We also had a program called NESAC there after the 9/11 incident, where we tried to study interdependent coupled infrastructure networks. that led to a program at NIH called the MIDAS program in 2004, and it continues to date. And this was the first program where a bunch of researchers were pulled together to study epidemic science questions and support policymakers. We have also been doing work with the DoD and other agencies here in the government. Our central focus is to derive data-driven causal models. It's become quite popular now to do this kind of modeling with AI and other related fields. But I think this is how we started doing these models, and you will see a glimpse of it as I describe the work we do. We're also very focused on questions that policy analysts raise, rather than just building questions for the sake of studying them. So let me start with the first project that was certainly a project that influenced my work early on. And this project is called Transcendence. It lasted for about 10 years at Los Alamos. Was transitioned. It's in the public domain now. Many studies were done with this, and it was the first large-scale transportation planning system that was developed, and was developed really to address important societal problems related to traffic flows and congestion, predicting household behavior, assessing social justice issues, and predicting the environmental impact of emissions. The questions really came from regional planning offices, organizations, and transportation consultants. And as I said before, it was developed in conjunction with them and finally transferred to these planning offices for use. And Argonne National Lab actually maintains an open source license. As I've heard last, they still continue to maintain it, although they have really extended and expanded on this quite a bit over these years. So in the picture here, you really see an output of a simulation of cars moving on the road. And this final picture looks pretty reasonable, but it takes a fair amount of effort to build out a model where you can track individual cars in this particular manner. Just to give you a particular example of what we use this for, this was the last study we did, where we studied traffic problems along with AECOM, a consulting company, around the White House. So there was a desire to close down what is called perimeter roads around the White House after 9/11 to reduce risks that might be incurred. So this was a issue that has to do with safety, but it would cause significant traffic questions to be popped up. And we studied this related to traveler experience, amount of time the travelers might take to travel, compare different solutions, and this outcome is actually documented in a report by the Planning Commission. It's called the WATS study, White House Area Transportation Study. You can look it up. What was key is that the way to study this was not by building aggregate models, but we built very detailed network-oriented models and then studied traffic as an outcome of individual level interactions. And I'll show this example by Epidemics, but keep this particular aspect in mind, and this will be the recurring theme in the talk that I give. The other part that I want to let you folks know is when I talk about projects, they are not small problems that I'm going to focus on, which I will of course do as we talk, but rather large programs that get funded and we work on it for a long period of time. So transportation work that I described was work we did for over 10 years and a team of about maybe 30 to 40 scientists. The infectious disease work is being done from 2004. Now it's 16, 17 years and continually improved. Similar work on disaster planning as well. And I think it leads to solutions that are eventually usable rather than one-off problems that one solves. Another example that I want to show you is how systems like this can be used to support human initiated or naturally occurring crises or disasters. And I bring this up because I think this is the kind of modeling that one could do using the lens of complex systems in India. For instance, hurricanes or what we call cyclones there can be studied, and we are indeed studying it right now for the US. This particular scenario was a scenario where there was a large explosion in downtown DC. It's a called the national planning scenario. It's a hypothetical scenario. And the key was to understand what such a large-scale disaster might lead to in terms of social, economic, and behavioral changes into society in the first few days after the event. And it turns out there's a lot of casualties in this, but nevertheless, many folks are still around, and we wanted to study how simulations and agent-based modelings over these networks can help do some kind of policy analysis. And we found some very interesting results. One is we found that communication system as it exists today can have a disproportionately positive impact on overall behavior. So back in 90s, when people had tried to study this question, cell phones were largely absent. Turns out cell phones can be used very effectively to try and bring people together, allow them to talk to their loved ones, and reduces the number of deaths in the models, leads to better health outcomes and reduction in anxiety. Of course, the policy question is how do you build self-forming communication networks that are very resilient to such disasters. Second point that we studied is that interestingly, the power network, of course, in the area where this event happened goes down completely, but one doesn't get cascading failures, and that's likely because of the supply and demand was set up in this particular region that will have to be studied for all different regions that we would take the problems further. And finally, we studied the question of emergent behaviors or composed behaviors, and we showed that personalized choices plus contextualized decision making and institutional policies really lead to emergent behaviors. And there's a nice article written in Science on this called Free Agents. You can take a look at it. Mitch Waldrop wrote it on the work we had done, and very nice examples were shown on how individual behaviors would show a certain level of adaptation as we go along in a simulation like this. So it's a big data problem. I don't think that this crowd needs to be told, but just to give you a quick sense, just to study problems in a place like Chicago, you have 400 square miles of area, 12 counties, 270 townships, 9 million people. The transportation network itself has about 4 million nodes and edges and 30 million trips people make every day. So you can get a sense for how big such a system can be if you want to study it. And we're going to try and study a particular class of models, which are I'd call network-based or interaction-based models. And the key ingredients are that you have individuals and algorithmic representations of their behaviors, and these are composed together via a network system. We largely try to use this as opposed to a model that is compartmentalized or aggregate models, not because they're not good, they're actually very useful, but there are many problems where this network representation turns out to be quite useful. I know Srini and Sayan and Sunita are also studying network representations in their work, and we can talk more about it later. So let me quickly tell you what a theoretical framework for this might look like, and then we'll go on to the particular example of epidemic science, which is something that our group has been deeply involved in for a while now. So here's an elementary theory of these systems. We call it graphical dynamical systems. I call it elementary because it's very simple to state. Lots of extensions are possible. I will mention them briefly later on. But even this simple framework, mathematical framework, makes it extremely interesting to carry out theoretical analysis. And as would turn out, theoretical analysis is actually quite hard for even such simple systems. So what's the framework? It consists of a graph. For now, we'll consider undirected graph. Each node can be thought of as an agent. Agent has finite domain to work with, and it has got a function that is endowed with it. You can think of the function as its behavior, the domain as the states it takes. Many interpretations are possible. If you use neuronal networks, then you have appropriate interpretation in that setting. And the idea is that you update the states of the nodes either synchronously or asynchronously based on your state and the state of its neighbor. So there's nothing really very different, right? This is basically cellular automata on a graph. But it becomes very, very rich when you allow graphical structure to be placed on it. The asymmetry really makes problems rather complicated. So what would a theory for this look like? First, of course, it's important to understand that what we are interested in studying is not the representation itself, but the dynamics that is basically implicitly represented. So what happens here is a system could be in state, here I've shown, I guess, ABC, and it moves from state 101 to state 010 with the local functions that I've shown here and written on the side. Or 000 might go to state 110. Computer scientists would view this as an evolution of configurations of a Turing machine. A physicist can just view this as states of the system. You can compress them as just number of ones and number of zeros. I know you folks have done a lot of work on statistical mechanics of this kind of thing, and that's certainly absolutely feasible and possible. But this is the basic study. And so the phase space in this is really nothing but how one configuration goes to the next configuration one time step. And a graph can be used to represent that as well. It's a very simple graph. It's a graph of where each node has one out edge and potentially multiple in edges. The number of nodes, if nodes take binary values in the original system, are 2 to the n, where n is the number of vertices in the graph, and the number of edges is 2 to the n minus 1. Basically, roughly it's like close to a tree, basically, right? So we don't have too many edges, because maybe 2 to the n edges, 2 to the n nodes, because each node has exactly one outcoming edge, basically. So one can study different functions on this, threshold functions being something that we have studied a whole lot. We've also studied symmetric functions. They're called anonymous functions in physics or game theory. We've also studied some asymmetric functions that I won't go in detail here. The point being that now you get a very rich class by changing how the network is set up, what sort of update schemes are used, and what sort of local functions are used. It turns out even this simple model generalizes a number of different questions and frameworks people had studied in multi-agent systems. Wellman's paper, for one thing, graphical models and graphical games that folks have studied in game theory, coordination games that Kleinberg has studied, very famous work by Granovetter on complex contagion, followed by work by Centola and Macy, can easily be represented in this simple framework. So that's the power of the framework. It's really simple, but yet quite powerful in terms of representing interesting phenomena. So what should a theory look like? The theory would really look like this in a nutshell. This is a computational theory. Physicist and mathematician would have an algebraic or a statistical mechanics view on this. I've taken a computer science view on this, given my training. So the question is, you really are given this representation of the dynamical system, and you are interested in studying certain properties of the phase space itself. Here are some examples. Does the phase space pi have a fixed point? A fixed point is nothing but a loop on this configuration space, right? You start with, say, 0, 0, 0, one time step, and you go back to 0, 0, 0 again. That's a fixed point. Or does it have a Garden of Eden state? Or does it have a state with at least 2 incoming neighbors? This is a classic inverse question. Can you count the number of fixed points? These are all structural problems about phase space. You can study design problems. You design SDS such that the resulting phase space would have certain properties. We've studied that as well. You can study control and optimization problems. You want to delete edges or vertices to modify the dynamical system so that it has desirable properties. So vaccination problems would fall in this. You want to delete certain vertices to make sure that the epidemic, say, doesn't spread in the network. You have inference problems. You observe the phase space in some form, and you want to infer the components of S, and I'll give you some examples. And the computational questions are really, what sort of algorithms can you design to study these problems? And what is the computational resources? Space, time, random bits, number of messages, to solve the problem as a function of the representation. The phase space is exponentially large in the representation, and that's the reason for all the interactability. So this is just a cartoon of what I said. We've written now close to 50 papers on this topic. I'm happy to send you a list, and we've just started. That's the point I want to make. This area is so rich that I think there's a lot to be done for folks who are interested in doing a PhD, and I just wanted to hopefully motivate this point for folks who are looking for dissertation topics. So let me give you some examples. One is, although the model is so simple, it turns out that GDSs are actually universal computing devices. If you have finite GDS, your universality is in terms of time and space complexity classes. If you have some notion of infinity in this, which means that the network is infinitely large, or the local functions are not over a finite domain, but oftentimes over natural numbers, then you can actually show in many cases that these simple systems actually are as powerful as Turing machines. And it tells you in often case by using this that to study the properties of phase space, you really have to do simulations. Or in other words, there is no polynomial time algorithm that can be used to come up with proper, easily solvable properties of phase space. Now, there are certain properties that can certainly be solved, but oftentimes basic properties remain very, very hard to solve. Finally, our results actually have shown a certain interesting trade-off between the structure of the graph and the local function. And there is a very deep algebraic theory by Robertson, Seymour, and others, Dick Stearns, Harry Hunt, Bodlander, and others, on what's called tree-width bounded graphs. I don't know how many of you know, but I think a lot of you folks might know about this concept. And the idea is these graphs have very small separators. And turns out many graph problems can be solved in polynomial time. The time and space complexity is polynomial, but it's really very large. But even so, it's a very powerful theoretical result that shows that if a problem can be written in monadic second order logic, then the problem gets solvable. It's like being able to write a linear program to say that now I can solve the problem in polynomial time. So this is a very powerful result, work done by multiple folks. What we show here is the start of a theory where you study dynamics over these kinds of networks. And now just tree width alone is not enough, but you need to restrict the local functions as well. And hopefully I might be able to give an example of this later on. So just one theoretical result, and then we'll move on to something else, or maybe a couple of them if I get a chance. So here's a classical problem computer scientists study. You're given a graphical dynamical system, and it starts with a state S, and you ask the question, can it reach a new state T in less than equal to R steps? Now, if R is written in unary, then you can just simulate it, right? You can just unroll the simulations or system and see whether T can be reached in less than R steps. But if R is written in binary, this is a very expensive operation. It turns out that in general, you have to do this unrolling. There's no shortcut for this. And so the formal result is that this reachability problem is actually p-space hard, even when these local functions are symmetric and Boolean. Very simple. But as a flip, if the local functions become threshold functions, which are a special class of symmetric functions, then the problem actually can be solved in polynomial time. And it is based on a very important observation that if functions are local functions are threshold functions, then the transient length in this phase space is actually bounded by a polynomial in the number of vertices and edges in the graph. So essentially, if there are n edges and m edges in the graph, then the longest transient you can get is roughly n plus m with some constants removed. That means that, and you reach a fixed point after that. So effectively, if you want to now study whether you reach a particular state, you keep unrolling it, you're guaranteed that after polynomially many steps, you will reach a fixed point. If your state T appears in one of these transient states, you're good to go. Otherwise, you say no as an answer. Very interesting result that shows your dichotomy, basically, which is what we are after. Here's another example of inference problem. What you're given is you want to study, you want to infer the local functions. You're not told what they are, but you want to observe the dynamics and study this. There's a very nice piece of work in AI on what's called active learning, where you're trying to learn some properties of this dynamical system by observing the dynamics. And there are multiple models of what observation means. One is a purely passive model where you just look at the unrolling of the dynamical system, or you look at it as what's called active querying, where depending, you ask a question to the system answers it back, and then based on the answer you receive, you ask the next question. So this is called active learning model, And we show that if you want to learn the local functions, and they are from the concept class either threshold functions or symmetric functions, and each query can return you the next state of the system, then in such a setting, you can actually use adaptive queries to reduce the number of queries you need to infer. So if you just want to infer the system without being adaptive or actually being an active query here, then you might take exponentially many steps before you can infer the local functions. But with this, you can actually infer it turns out the local function in roughly number of queries that relates to actually interestingly certain kind of colorings of this graph, but it's lower bounded by the number of the maximum degree of the graph and upper bounded by square of the maximum degree, but it's really upper bounded by what's called x of chi of g squared, which is really distance to coloring of this graph. So rather interesting structural characterization of how distance to coloring of graphs connects to these dynamics. So let's go to some real world problems in the time I have, and then we can take questions. So I'm going to focus on epidemics, partly in something that you all now know very well, given this COVID has been with us, unfortunately, for more than 1.5 years. And this is a well-studied problem. People have built mass action models for epidemics for, I would say, over 100 years. But even before that, Bernoulli's work essentially had all the ingredients of building such models back in 1700s when he was studying smallpox and eradication of it. And then these compartmental mass action models, you write a set of differential equations and then study how the mass in S would be transferred to I from I to R with a set of differential equations. For this crowd, I don't think I need to tell you much in detail about it. They're fairly direct differential equations. But even such a simple model actually is very, very powerful. And epidemiologists have studied this in a big way. Even for COVID, in the last 1.5 years, there have been at least 6 papers in Science that use models such as this. They are, of course, extensions of this basic set of equations I've shown you, but still compartmental models. Brian Grenfell and his colleagues at Princeton, Simon Levin, Shadi, and others have produced some remarkable work in the last year on this topic. We are going to take a slightly different approach. We are going to study networked epidemiology. Again, something that now many of you probably have already started studying. I know that there's a number of groups in India who study this, and people in the audience might already be studying it. But just for others, we have a network. We have nodes, just like we described for GDS. Each node now can be thought of as an individual. Edges represent interactions or social proximity. And labels on the edges tell you what is the probability of transmitting a disease from an infected node to a susceptible node. So red nodes are infected, R is recovered, S is susceptible. And the basic model is where you start with a node, single node here in this simple example of an infected node, and tries to infect its neighbors independently with probability 1/2. It could be other probability as chosen. In this particular case, V infects V1 and V2, but leaves V3 untouched. V1 and V2 then try to infect their neighbors. They are successful in infecting V4 and V6. V5 is untouched. And finally, V6 infects V3. V0 does not infect V3 in first step, it turns out. So you can write down the configuration of the system as I, all others in susceptible state. I recovers. In this model, we have recovery time of 1. That's just for showing you the example. In general, recovery time is more than 1. So this is really a graphical dynamical system. I'm sure you can see the correspondence between the theoretical framework that I described. So just like phase space, what you have as an outcome here is a dendrogram, but the representation of phase space for probabilistic system is a Markov chain. The key aspect is this Markov chain is extremely large. So I've just given you a fragment of this chain. If you have a graph of n nodes with SIR model running, the Markov chain has 2 to the n nodes and 2 to the n edges. Actually, more than 2 to the n edges, many more than 2 to the n edges. Depends on how the probabilities are set up. And so studying the properties of this Markov chain becomes really complicated and hard in general, as your intuition might suggest. So here are some theoretical results again. If you want to study reachability question with this probabilistic transition, then the problems start becoming hard even earlier. And there are very simple complexity classes that have been studied in the literature. People, we show that this problem is what's called Sharpie hard because you're talking about counting problems here. So again, simulations become necessary in this particular case. We can study inference problem. In case of this problem, we're trying to infer the transmission probabilities. It turns out you can actually infer these transmission probabilities with active queries and get what's called a bicriteria approximation algorithm. I won't go through it in detail. I can share some papers on this for you folks. So what I'll do is in the next time, I have about maybe 10, 15 minutes, I'll describe what we are doing in the real world, because all this theory is nice and fine, very interesting. Personally, I really enjoy it. I'm trained as an algorithmist and complexity theory person. But as I've tried to put this into practice, I've also realized that one needs to work very closely with practitioners and work on real world problems to try and study this. So the first question, I did my work in theoretical computer science. And when I wrote papers for the first 10 years, I would write a class, papers would always start by saying, I've given a network and I study some properties of the network. I wanted to say Steiner trees or spanning trees. The problem is if you want to study epidemics, you don't have a network, and building such a network is actually the hardest part in many ways. There's no network that is available. Infinitely many measurements are not going to solve this problem. How do you analyze the dynamics? It turns out to be a hard problem. How do you design interventions to try and prevent the epidemic from spreading? Problem again is mathematically elegant solutions are okay, but they are oftentimes not implementable in real life. How do you forecast the dynamics? Again, hard, partly because ground truth is very noisy, incomplete, and time lagged, but even more so as it happens for any social system, and this is one big difference between physical systems and social systems, is our actions are endogenous to the system, including the forecast. So if I say that things are going to be really bad in the next 2 weeks in, say, Chennai, perhaps people would change their behavior and lead to a smaller outbreak, and then you might say your forecast was wrong. It's not clear whether the forecast was wrong or people adapted their behavior to change the outcome of the disease. And this becomes a very complicated question when you study social systems. So we are going to try and build these kinds of models. We've been studying this for a while and actually synthesize networks from some 1994 onwards on which such models can be carried out. And the synthesis of these networks is based on a work that we started, as I said, back in the world of transportation planning, where we essentially build a digital twin of a city or a region under consideration. So if I want to study Chennai, then I would look at census data, I look at phone log data whenever available, I look at building data sets, I look at travel diaries that are available at least in the US and now in India as well. I would look at information on schools, colleges, commercial locations, and then I essentially build a network in which an individual and their is built out, a family for the individual is built out, and the individual in a normative day moves from one place to another, trying to fulfill their daily activities. The key aspect of such a network is that if you look at the network and try to find a person in real world in this network, you won't find that person. That's not the intent at all. On the other hand, if you look at statistical properties of the network, you are hoping that the statistical properties of the network are very, very closely related to real world social contact networks and populations themselves. And I have a number of tutorials that myself and others have given. You can, I'll give you links and you can take a look at it. But this is a program that's ongoing and it's a subject of its own in many ways. We then build simulations and then do analytics on top of these networks. What it gives you is networks that they're multiplexed and co-evolve. Multiplexed in many ways. There is layers, there are individual and their behaviors, there are households and their behaviors, there are communities, and communities are embedded in regional systems and then national systems. A similar thing happens, by the way, for other socio-technical networks too. you have infrastructure networks, and then a set of behaviors that go along with them. So this layered multiplex aspect becomes really crucial here. And you can use this to study a number of problems, from studying analysis problems, such as the one I stated, or forecasting problems. You can study the problems of situation assessment. You can do economic impact analysis, intervention analysis. You can study inverse problems, trying to discover patient zero, for instance. And what we have done over these years now is to build pipelines to support it. This is just one example of how our pipeline runs on supercomputers here at Pittsburgh Supercomputing Center and our place. I won't go into details, except to say that you have to run a large number of simulations effectively on a very short period of time to come up with these analytics. Why are we doing this? Of course, it's scientifically very exciting, but all the questions we have undertaken really are questions that have been posed to us by agencies that we work with. So we work with a number of federal agencies, including Department of Defense, CDC, Department of Health and Human Services, NSF. We work with Commonwealth of Virginia. We used to work with the Department of Health here, Department of Emergency Management, Department of Education. We are the primary modeling group for them. And we work with local agencies, our universities, other local universities, the hospital systems across the state. They have an association, 140 hospitals are a part of it. And we started doing this back in late December, early January, where initially we just did qualitative studies. But by March 1st or so, we started really engaging for the COVID pandemic. And we've been essentially briefing these agencies every week for the last 60 plus week now. And about 80 of us work on this. It's a continuous effort. It's very intense. In some ways, very satisfying, in other ways, very tiring. But it's important to do this. And I think there's some very interesting lessons to be learned from trying to support an ongoing disaster or crisis using scientific methods and trying to essentially discover new ways to do it in real time. So here is how, for instance, our reports look like for the state. These are all on the web. You can take a look at it. They're very transparent here in the state. We'll give them reports that have to do with weekly updates. We'll give them forecasting results. We give them scenario updates, such as doing what if analysis. What if people change their behavior? What if you put in certain restrictions in place? What if you remove certain restrictions in place? What happens if more people take vaccines? What happens if you wear masks? And so on and so forth. So all of this is studied. Every week we would do this and give them updated results. And this is used by them. We are not in the business of setting policies. We are basically providing them scientific basis, which they can use then, along with other considerations, important considerations, to decide and formulate and effectively apply these policies in the real world. So final thoughts. I think that this elementary theory of networks in graphical dynamical systems form is really quite powerful. And I encourage folks to study it further. Lots of interesting questions. I think in real world, one has to combine theoretical understanding with data and computing systems to support policy making. And I'll end with the direction that we are really trying to take this work, which I think is really important. As more and more people get phones or other devices, we think that the next round, and we are actually starting to see this in many application areas, including disaster management. People want information. People want to be able to make decisions, and decision makers are not just government decision makers, right? Mother and father is a decision maker too. They decide whether the child is going to go to school or not. They decide whether they're going to work or not. They decide whether the family is going to wear the mask or not. So the concept that we want to try and sort of popularize is what I'm calling it P-cubed analytics, which means on one hand, decision makers should have information that is pervasive and should be able to make decisions at any time, any place, and with any device that they have. So this is a very classical idea of WISER in computing, where they call it pervasive computing. So basically access to data and computing and systems should be pervasive. Second is the decision maker should be able to make personalized decision. And personalized means they reflect their context. So they might be in a family which might have particular social income, economic constraints. They might be in an area where the epidemic might be much more, numbers might be much more high than other places, and so on and so forth. And finally, precise. They want to be able to make precise decision, but also want precise information. And I think that as we go along, this kind of analytics is what is going to be consumed at a population level. We're already starting to see information through Fitbit or Apple Watch being given to individuals. There is a lot of interesting future work people are thinking about. Apple Watch, for instance, they're giving you lots of different signals. They're talking about providing you information that might help you make better plans and hopefully reduce the probability of any chronic diseases. People in disaster world can actually use this to understand if there are people around them who might be sick through these devices. So much use can be made out of these devices, and I think it's a really new world that we're entering. So with that, I'll stop, Srini, and hopefully take questions. It leaves enough time for doing that.
That's wonderful, Madhav. Any questions from the audience? I think somebody had a question in the chat box.
I can't see, so maybe I will stop.
Okay.
One sec, let me try and bring it up. Okay, so here are some questions. So Hari Prasad has a question. For function inference, does the function at the node need to be Boolean? Hari, good question. The positive results we had were for very specific class of Boolean functions, either threshold functions or symmetric functions. In general, that doesn't have to be the case. It turns out problem quickly becomes very hard in terms of provable results. A heuristic certainly can be applied. The second question was, any examples of intervention that were implemented based on network study? Excellent example question. So whether they implemented it or not, I do not know, but I can tell you what we did, and that was picked up. So one thing that we did using these network models was to support states analysis on contact tracing. And we showed how contact tracing was valuable for them, because you contact tracing, I don't know how many of you know the problem, but the basic problem is if somebody comes, you pick up a person who is sick through a process of interviewing, and then ask their who their contacts might be, either through digital apps that we have. Arogya Setu is one in India, but it's not used apparently. But in general, if a lot of people use it, certainly that can be used. But you can ask through interviews, and manual contact tracing is viewed very important way. But that particular way of doing analysis really requires a network representation. So we were able to show them what value they might derive, how they can increase the number of contact tracer, and how they can use the increased contact tracer to reduce the disease prevalence. We also help them deciding whether the contact tracer should be increased or initial people who took the information on cases should be increased, for instance. So that was one example. Another example that we have studied is vaccine allocation. The paper is on medRxiv and it's being submitted. And this has been a result that I think is really very powerful. I still hope that somebody picks it up. I have been in contact with multiple agencies, including national and international health agencies. And the idea is, who do you vaccinate? So the network model provides a very intuitive result, which everybody would agree is interesting, which is vaccinate high degree nodes, right? People who have large number of social interactions. The crucial part is the networks are used to do the analysis, but when you want to finally implement this policy, it turns out very simple questions can be asked of individuals and be used to vaccinate these folks. Our actual results show something very remarkable. You don't need exact estimation of individual degrees, because that's very hard to get. So it's an example of implementable policies that you can construct. So just two examples, there are many others. Again, Hari, the important point is our job is to do the analysis. Whether finally that gets implemented is not something that is clear. There are many other reasons some things don't get implemented. The last thing that we are doing using network models is actually trying to place vaccine allocation centers, distribution sites that are mobile and are based on traffic flows using data from phones.
That's
Any other
wonderful. Any
questions?
other questions?
Yeah, so Rinkaj,
Yeah.
yeah, there's a question how agent-based modeling is complementing the growth of network science. So Rinkaj, I think we use agent-based modeling in conjunction with network science. I don't view them separate in some ways. After all, agent models we study are basically models over networks. So in that sense, networks are a crucial part of doing agent-based modeling. And understanding dynamics of networks are really understanding dynamics of agents. So in that sense, they are really going hand in hand in many ways. You also asked, agent-based models are often being cursed or amplifying one aspect of the problem, possibly. And there are weaknesses too. Let me also say, since you bring this up, Rinkaj, that models of this kind are not free of problems, right? OD models have their strengths and weaknesses. This class of models has a strength and weaknesses. Oftentimes has a large number of open parameters. Building these networks is very complicated. Running them on HPC is rather hard and non-trivial. So yes, they come with their own sets of problems, but I think they provide intuition and information for real world questions that are slightly different than compartmental models. Which model you end up using really depends on the final use and the time you have to do it.
Any other questions? Madhav, I have a slightly generic question, if it is okay.
Yeah, please.
Can you model the spread of literacy using these kinds of models? Because India literacy is still a problem, pretty low. So can you optimize
Right.
literacy programs using models like this?
It's a good question. I never thought of it, Srini. In general, social scientists have studied and looked at other kinds of, transmission of phenomena. So to the extent literacy is dependent on network effects, one can certainly do it. For example, smoking is one where network effects have now been documented. Obesity is another one. So if you can argue that your ability to pick up, go to school, or one's ability is to pick up the opportunity to go to school depends on peer pressure in one form or other, then certainly are in business, right? But that first needs to be shown. In general, my intuition is yes, peers definitely affect. If multiple folks in a village start going to school, the child almost certainly and his parents are likely to feel the desire to send their son or daughter to school. So I think it's absolutely possible, but I have not studied it. It's a good question to think about, I think.
Thanks a lot.
Yeah.
If there are no further questions, Sayan?
There is one more from Harishankar, if you want me to take it.
Please go ahead.
Yeah, it says, as a continuation of the previous question by Hari, is it possible to pose the inference question problem based on problem physics to calculate the probabilities for networks? Didn't understand the question very clearly, Harishankar, but if the goal is to understand certain properties of the networks itself, then yes, you can actually use this setup to pose the problem. Sometimes, you can solve it analytically or algorithmically. Sometimes you cannot, and that's something that would be a research question for you folks to undertake. In general, I think these inference problems are a beautiful class of problems where you're trying to infer properties by viewing this as a black box, by essentially probing it. And there are other applications where this works out. It turns out to be very interesting in many ways.
Any further questions? So, the no further questions.